Dear students, I am giving the 10th and the last video on topology 1. That is about the totally disconnected spaces. What do you mean by totally disconnected spaces? Definition: a topological space X2 is totally disconnected provided that each component of X is a set consisting of a single point. A topological space X2 is totally disconnected provided that each component of capital X is a set consisting of a single point. Example, a set capital X with a discrete topology is a totally disconnected space. Theorem, first theorem, the product of totally disconnected spaces is again totally disconnected. Proof: assume that x alpha to alpha is totally disconnected for alpha in the index set. To prove that pi x alpha, the product pi x alpha is totally disconnected, let C be a let C be a connected subset of pi x alpha. Consider the projection map pi alpha from the product space pi x alpha to individual space x alpha. Since pi alpha is continuous and C is a connected set, then pi alpha of C is a connected subset of x alpha. But x alpha is totally disconnected. That implies pi alpha of C is a one-point set. This is true for every alpha in index set. That shows that C is a one-point set. Hence, pi x alpha, the product space pi x alpha, is a totally disconnected space. That's what about the proof of that theorem. Coming to next theorem, statement: every subspace of a totally disconnected space is again totally disconnected. Every subspace of a totally disconnected space is again totally disconnected. Proof: let X2 be a totally disconnected space and let A to A be a subspace of X2. Let C be a connected subset of A, then C is a connected subset of capital X. Otherwise, what will happen? This is what is given in brackets. Otherwise, C equal to U union V, which is a separation of C in capital X. That is U V elements of tau, and C subset or equal to A implies U subset or equal to A and V subset or equal to A. That implies U intersection A is equal to U and V intersection A is equal to V. This implies U and V are elements of tau A, the subspace topology. Then result 1, that is C equal to U union V, forms a separation of C in A. That is U and V form a separation of C, which is a contradiction. Hence C must be a one-point set. What is the reason? Since X2 is totally disconnected. That implies A to A is totally disconnected. Next definition: a topological space X2 is zero-dimensional if for each P in X and for each neighborhood U of P, there is a closed and open set capital V, such that P is an element of V which is subset or equal to U. A topological space X2 is zero-dimensional if for each P in X and for each neighborhood U of P, there is a closed and open set V such that P is an element of V which is subset or equal to U. Next definition is T0 space. A topological space X2 is a T0 space provided that for each pair of distinct points there is an open set containing one of the points and not the other. Example, Hausdorff space, that is you are taking two distinct points x and y and u and v, two open sets in capital X, and u contains x, v contains y. A topology space X2 is a T0 space provided that for each pair of distinct points x not equal to y, there is an open set containing one of the points. So the point x is there and u is an open set containing this x and u does not contain y here. Therefore, a Hausdorff space is an example for a T0 space. Next theorem, every zero-dimensional T0 space is totally disconnected. Proof, let x2 be a zero-dimensional T0 space. Let C subset or equal to x and A and B be two distinct points in C, but x2 is T0. Therefore, the X is an open set U such that A in U and B not in U. Again, x2 is a zero-dimensional. That implies that X is a closed and open set capital A in X such that small a is an element of capital A which is subset or equal to U. Then what will happen? A intersection C is both open and closed in C. And moreover, small a is an element of A intersection C. Since A is an element of A intersection C, we have A intersection C is non-empty. Also B is in C and B is not an element of A intersection C implies A intersection C A intersection C is a proper subset. That is, A intersection C is subset not equal to C. This implies A intersection C is a non-empty proper subset of C which is both open and closed. That implies C is not connected, which implies x2 is totally disconnected.